start. Hello everyone, welcome to another event of our UD Mobility Forum. You know, over the past 3 days, we probably have attended multiple talks on diamond. I promise you, this one will be a special and very interesting one. So today, it's our pleasure to have Dr. Pei Zhou from Brown University to join us to give a presentation on UD Mobility Forum. Dr. Zhou right now is assistant professor at the School of Engineering at Brown University. She received her PhD in computer science from UCLA and PS from the Southeastern University. Her research investigates architecture, programming abstraction, design automation tools for the configurable computing and heterogeneous computing. She has published over 40 papers in top-tier computer system and the design automation conference and the journals. She has won multiple best paper awards and the best paper awards nominees. So without further ado, let's welcome Dr. Pei Zhou.
Thank you, Dr. Gao, for the great introduction. And thank you for Dr. Shi for inviting me in this University of Delaware. And then actually, I have been like anticipating for this trip for so long. Once I hear this, I should be here in May, and I start to feel like I cannot sleep last night. And then it's very great. Like I met with several students here, and then working touring on those autonomous vehicle car. I think that's fantastic. So this is a great chance for me to introduce a little bit about my research and also introduce some of the exciting projects that's actually being collaborated with Dr. Shi and also Dr. Dong on this accelerator customization in the real-time and the safety critical system. Actually, I will be focusing on the first part of this talk into all about the customization. What is customization? How we can do such kind of a chip customization for different applications. And then I'll be focusing actually discuss about the latest publication and also exciting project we are working on how to integrate such kind of system for real-time safety critical system. So that will be the two focus for today's talk. Okay, so I spent 7 years working with Professor Jason Kang at UCLA to get my PhD degree there. Before that, I was a ECE background in Southeastern University, Wu Honor College. And then I figured out I really want to take a taste about what the real industry product is. So I went back to China, working as a senior software engineer in a hardware company. So this is where we compete with NVIDIA. And that time, we want to do the best AI training chip in the data center. So that's V100. That's our competitor at that time. And then we launched our second generation AI chip, which is compatible with the directly competing with A100. And then I joined the Pitt ECE. And then last September 1st, I bring all my students from Pitt to Brown University. My research focus is from 3A, from the top level to the down level is abstract application, abstraction, and then architecture. So I built all those different hardware circuits on either AI chip, that's ASIC chip backend, or we prototype all those designs on FPGA. So FPGA stands for Field Programmable Gate Array. And some of you might have this digital design courses, and then you will deploy some of your design in those FPGA chips. But then FPGA nowadays is not just a FPGA. They are actually a combination of all kinds of customized chips. We can integrate those AI Tensor core in the FPGA. We can integrate the CPU in the FPGA chip. We can, in the future, probably we can also integrate those PM processing memory and also other, let's say, optical sensor processing units also in FPGA chip. But there's just so many ongoing exciting trend in integrating in FPGA. And also we not only design circuits in the FPGA, we also learn how to better or easily program FPGA in an agile development way. So one example is that how we can do FPGA design in an hour without a few weeks. So that's our focus on compiler. And then that's application. Well, with all those tool chain we develop, then how we can better support different kinds of applications. So I give two examples here. One is artificial intelligence. Another is genomics or medical. I'll explain more in later slides. And I'm also teaching the undergraduate course and also graduate level course. This semester, I'm teaching VLSI course. So we actually put all those 32 students to publish their ASIC chip design and then ask them to post their chip layout after at the end of this semester. So that's the VLSI course. So this is actually one slides I love the most, I would like to share with everyone. Why we need the customized computing in the first place. So this is a chart that shows that with this development, so x-axis is the different technology node, semiconductor technology node. And y-axis is this volts per square centimeter, which means that the power density. The higher means that the more power or the more energy dissipated from this chip system. So this one is a log scale, which means that if we have a linear line here, which means the power density there is like a growth exponentially, right? And then the point is that if we keep scaling this chip performance without capping, put a limit on this power dissipation, then we'll face a challenge that the power or the heat density within the surface of the chip is higher, even higher than nuclear reactor. So we cannot afford such kind of thing. Also, this one is like a sun surface, right? So this is not good. How we can sustain those chip performance without blowing our chip? One way is to do using parallelism. Actually, this is how this in the 1990s that where we have those multi-core CPUs, and then nowadays we even have those thousands of cores GPUs, right? So this is how like parallelism can help us to still scale out the performance by keeping those power dissipation under control. Another fold is customization. So this is we adapt these circuits architecture to certain application domain. We can design our own chips. This is not from a general purpose CPU or general purpose graphic processing unit. We can actually design our application specific chip, and then they can bring us further like energy efficiency. This can be like as high as 1000x energy efficiency compared to those general purpose computing. So that can greatly improve those overall system efficiency. And why we use FPGA in this for this customized computing? FPGA, programmable gate array, can offer us this kind of like a huge improvement in terms of those energy efficiency. So in terms of this is a number that I get for this prior generation, like comparison latest study. This shows that we can even achieve higher than that. That's more than like a 100x, even like 1000x than CPUs. And then the overall architecture stays like this. So we have those programmable memory, and also we have those programmable logic. This is a lookup table. You can kind of think that given any like this k inputs, I can configure this functionality of this lookup table to different function. So if this is a 5k, that's k equals 5, that's 5 input. I can have a combination of like 32 different combination of those logic I can describe. And then there are hundreds of thousands of such like lookup table in those chips. So we can basically reconfigure this chip to any functionality we want to implement. With those this distributed memory, and we can also allow those different data on-chip data memory management. And also we have those flexible I/O interface and input and output. Then we can reconfigure the data depending on this application scenario, and then we can feed a different let's say the sensor input to fit into the I/O or memory port to those I/O. So these are like the flexibility provided by FPGA. We can allow those flexible compute. We can also allow flexible communication. So that's the overall architecture about FPGA. And then we have been successfully using FPGA for many different applications. And then one example is how we use those FPGA as the computing platform to accelerate this 3D registration kernel. That's one of the most time-consuming kernels within those 3D reconstruction that's in the medical imaging applications. And then at that time, we have been working on this using this is a overall architecture, circuit architecture about those image processing kernels. You can kind of think that, oh, image processing, we are doing this, let's say the average or filtering or like denoise by using the neighboring pixels, right? So there's a huge like a local data reuse. And with FPGA, we can build circuits that can do the best to better utilize all the neighboring like pixels, and then build those customized data forwarding chains so that once I read the data, I use it as the most as I can, and then when generate the output, I like send them back to the DER. But this cannot be easily done in CPU or GPU or this, let's say, memory or cache-based system. By using FPGA, we can build this data forwarding modules in the chip. And this is another example when we use FPGA for those genome acceleration kernels. So one of the kernel in our nowadays, the genome application is this sequence aligner. So you see the whole human genome has like billions of like gene pair. So this gene pair is like ATCG, right? But then when we do those blood tests or those gene tests, we are actually sampling those little like sequence. And then those little sequence from the sequence aligner output is only a few hundreds of base pairs. So we have to align those base pairs across over this reference genome. So that's where we need to use a Smith-Waterman algorithm. Long story short is that the Smith-Waterman algorithm is a dynamic programming algorithm. So we can allow, if we can design, let's say, a DP algorithm accelerator on FPGA, we can greatly improve the efficiency when executing this Smith-Waterman algorithm. And then at that day, we managed to reduce those Smith-Waterman algorithm by using CPU to 10 hours to a few like minutes. So that's the scale of about hardware acceleration using FPGA. So these are all like existing accelerator we have been deployed. By the way, this one is also deployed in UCLA Medical School nowadays. Another example successful story is Microsoft Catapult project. So whenever we use Microsoft Bing these days, actually can be powered by those FPGA cloud data center servers. Microsoft launched this Catapult project, I think in 2012 or 2013. And I was fortunate to join them in 2014 summer as an intern to do this kind of effort. So in Microsoft, they use these thousands of data center servers to host these FPGA chips. And then when they want to do deep learning or Bing search or data compression or decompression, this kind of application, they are actually using FPGA for such kind of like deployment. And this is a board they use, that's an Altera board. So there are two big giant FPGA company, Altera and Xilinx. Xilinx later acquired by AMD and Altera later acquired by Intel. And this is the architecture where this FPGA actually talks to another FPGA through those optical interconnect. Instead, we do not have to necessarily go through the CPU. So FPGA talks to each other directly without the intervention of CPU. So that reduces the latency and also improve the efficiency. So that's a successful story, right? But then you may wonder, how can I think I have give you enough motivation about this benefit provided by FPGA or customized computing on FPGA. Then how we can program such kind of FPGA? Can every programmer, let's say the audience, we all have taken some of the C++ courses, and then can we program FPGA? Or I have never touched the RTL programming. I do not have a digital logic circuits before. Can I still program FPGA? So the answer is yes. Nowadays, we program FPGA not necessarily from those circuits or register transfer level. That's the RTL level. You do not have to write to Verilog code or VHDL code. We actually write those design in using C or C++. And there are tools called high-level synthesis can generate the RTL circuits from the C or C++ code. So, for example, this is the C code for this stencil. That's the image processing, which we just described. When we need those neighboring 4 pixels, we can actually define using this 5 nested for loop. And then this is the input, left and right and up and side, up and down, and then we can get those values and then apply some constant, and then we can generate the output. So this is actually the behavior description, right? We just described this algorithm. This is 5 nested for loop. But then with high-level synthesis, we can apply certain parallelism and pipeline optimization to this description, and then can generate the circuits and generate the RTL, and then using the backend implementation tool, this is the actual circuits or layout when implementing all those circuits on FPGA board. So we highlight a field control logic here. So those chip area, this part is like over 70% of this chip utilization. And then we can do this fast or agile development on FPGA by using high-level synthesis. So I think FPGA give us a great platform to do this fast development and then reduce the design cost, because then we don't need that long time to wait for the chip. For example, if we're using ASIC chip, then once we send the design file to the fab, at least we have to wait a few months before the design has been sent back. But then with the FPGA, we can deploy that right away, right on site. Time to silicon is within a day. So that's the beauty of FPGA. But the thing is that we really want to guarantee that this platform is good for the, let's say, most of the application, or let's say one of the most popular algorithms nowadays, that is the deep learning, right? So when we revisit these or re-examine the energy efficiency about FPGA versus GPU versus CPU in terms of deep learning inference, we also did this study to show the energy efficiency. So this GWatts per watt means that GOPS per watt means that with 1 joule, how many operations I can operate. So the higher number this is, the better efficiency or the power efficient this system is. So I put 3 or 4 different applications. You can all kind of think this is some vision transformer for classification job. And then there are 3 different bars. So the first bar is the GPU. And then the second bar is the FPGA with the same technology node generation versus this GPU. And the third one is, let's say, 8 nanometer, a newer generation of GPU. And then which one is the best from this chart? The 8 nanometer GPU, right? So it's best for 2 reasons. First of all, it has a more advanced technology node, but even under the same technology node, this one, FPGA, is not as good as the GPU, right? So why is that? Why FPGA in this case becomes the most inefficient platform in deep learning inference? So I'll explain a little bit, and then I'll show another figure that actually flips the result back, which makes FPGA the most efficient platform again. So don't take pictures of this one because this is not the latest one. Cindy, I know you. Yeah. So if we re-examine this, if we want to explain why GPU now is good in deep learning inference, is that they keep introducing those microarchitecture change. In this case, that's the Tensor. So since 2017, that is Volta architecture has been introduced. They put those not only the vector instructions in the GPU, but also the tensor operation. That in this case is tensor cores within the GPU microarchitecture. And then with tensor core, they can compute 128 operations per cycle instead of 16, let's say, operations per cycle compared to the vector instruction, existing vector unit on GPU. I will just put some number there. Let's just give you some idea. It's not accurate, but then that's the same scale comparison we're discussing. And then they keep throwing new those tensor core microarchitecture updates. So this one, V100 to A100, we see a huge jump, right? That's from B prime to C. And then from A100 to H100, that's a Hopper architecture. We see another huge jump from C prime to D. So they keep updating those micro architecture. But then from the B to B prime, that is, they are keep improving their software compiler so that they can generate a better code that runs on those tensor core. So that can explain this increased performance, right? So what if we have an architecture with those tensor core also, so that we can map those deep learning inference or those matrix multiplication kernels on those tensor core as well, right? So be prepared to please take pictures of this one slide. So that's exactly, there's a game changer FPGA. That's the latest release of FPGA. And then with our development framework to generate a code that maps on this kind of architecture, FPGA plus tensor core, now we become the highest energy efficient platform again, which also this translates to about 10x, 8x to the 8x, 10x compared to the latest GPU. So this one is the SSR is our framework name, but then the chip is actually the same technology node, it's 7 nanometer, and it's the same technology node with this A10. So it's like a fair comparison. So this 10x energy efficiency again is how we achieve. So what is this XFPGA and how we can achieve, how we can design a compiler that generates the code that can work perfectly on this XFPGA. So that's our secret sauce. So first of all, what is this XFPGA? XFPGA is the AMD Versal ACAP architecture, adaptive compute acceleration platform. And this is an overall architecture of this chip. So we have those CPU as the general processing units there. We still have this programmable logic. You see all those LUTs, and then on-chip RAM, these are long-chip RAM. CLB is like the LUT, and the DSP is these, previously we used DSP for those MAC multiply accumulator operations. But then the highlight part is here. They have an array, that's a 2D array of AI tensor core integrated on the same system chip. So this is within the same chip. We have those AI engines. And each AI engine, here we have 400 of those. And each AI engine is a very long instruction word processor. You can kind of think that these are very similar to tensor core. And then we can now map those deep learning algorithms on those tensor cores, right? So I would like to highlight two work that we have been achieved on using this half work. The first one is composing diverse accelerator for matrix multiplication. This is how we achieve those super-driven optimal design on those XFPGA, this ACAP architecture. And second one is that how we do those end-to-end application. So not only we can accelerate the matrix multiplication kernels, but also other non-matrix multiplication kernels within those end-to-end deep learning inference. Because we probably have heard that if this is in CNN network, we have batch normalization, right? If this is a vision transformer, we have softmax, we have layer norm, we have the other non-matrix kernels. So these are some of the work we have been already achieved, and then we can do such kind of end-to-end deep learning inference on using our proposed framework. So I think we all know that these are just a huge demand for those deep learning inference. But then if we take a closer look at all those deep learning models and then plot their different kernel shapes, then we can visualize this different shapes. When I mean shape, that means the compute kernel size or the tensor size. So this is one visualization about this, how large or how small those matrix kernels within a vision transformer model. If you see this thing like piled of a little circle, actually that means they have many small matrix computation within those end-to-end vision transformer. But then these are like 5 large disk, means that they have only 5 large matrix multiplication kernel within this. But if we want to map such kind of thing on GPU, how GPU program this? So actually GPU will build each this little circle as one single kernel, and then I'll use all those GPU resource for each kernel. So it can be the case that we have done a great job in accelerating those large circle, those large shape kernels, but then the utilization for these small kernels is just very small. It can be as low as 1%. So we're wasting so many resources when compute such kind of deep learning inference on GPU. And actually that explains a little bit about why GPU is not giving me this full utilization all the time. It's because of this mismatch of those shape, those kernel shape, and the underlying hardware architecture, right? So that's the reason. And actually that's also exactly the reason why in the first place, when we want to deploy vision transformer on this ACAP architecture, we also face a similar situation. That is, the utilization is very small. So this one is achieved performance of 49. So this is less than 1% of the total achieve or the peak performance. But then with our clever framework or this development, we greatly improve this utilization by 32x, and this one is 25% of the total chip utilization, which is a huge step from this 1% to 25%, right? But then also I will mention later that this is not 25% is not the limit. It really depends on these different models, and also we can do optimization based on this version as well. But this is just one vision transformer example. So I think we now have some a background or idea about, okay, if we have those vision transformer, or if we have a machine learning model which has a huge matrix and a small matrix, then we should develop some way so that we can make better use of the whole chip resource, right? And the whole chip resource contains 2 parts mainly. One is the computation resource, and another is the off-chip communication. That is how fast we bring in the data and then kick out the data. So this is off-chip communication. And those different shapes of the matrix, they actually have different requirements. Those large matrix, they need huge computation, whereas the small size of matrix, they need huge communication. This is not just the volume, but then the ratio. So they need a huge computation versus communication ratio. And if we have such kind of imbalance or this situation, how we can better utilize this whole on-chip resource or an off-chip communication resource. So we certainly cannot do this. So this is our baseline design. That is that we design one single accelerator, and then we, in order to finish all those computation, maybe this matrix is too big and then it cannot fit on those chip. We have to do the tiling. That is, we cut those huge matrix to smaller one and bring them in tile fashion, and then compute those in tile fashion and send the data out. That is the final result back to this off-chip DDR. So that's the these general programming model. And then this is where we feed the data from this programmable logic to the AI tensor core to do this tensor operation, and then send back the data to those programmable logic, and then use the program logic to send the output back to the DDR. So that's the general framework, but we know that it's not good mapping strategy. What can we improve? So actually we propose to improve this by, so this is another like animation to show that if we want to use one single accelerator for this small matrix modification, then we have huge waste, because basically we'll do padding and then use those same like large accelerators to compute the smaller shape. Then that will cause huge like waste in terms of the compute, and also huge waste in terms of communication. So that's not good. And we know that's not good. And then we really want to achieve this high utilization. So this is a picture where we finally achieved that we are utilizing more than 90% of the total tensor core resource. But then how we can achieve that? I'll skip this one slide. But then the key idea is that we use diverse accelerator. So think about this. So we can partition this on-chip resource as flexible as I need, because we have a customized I/O, DSP, those on-chip buffers, and then on-chip logic. What about we put one large ACC and then another small ACC, and then allocate those different tasks or different kernel shapes into those different accelerator? In this case, I put two diverse ACC in the system. And it's good because this large ACC, they can take care of those huge matrix modification, and then they can do a very good job in those data reuse. Whereas the small ACC can take care of those small matrix, and then now we can like we do not necessarily need to do padding. We do not necessarily to pay the overhead in the wasting resource in computation and communication. So we achieve the better of the both worlds, right? We want to take care of all those computation. So that's exactly how Charm has done. So Charm has provided, first of all, Charm has provided this accelerator design template. That is, we can generate those diverse shape of ACCs, and then we can also allow user just to give me this like a deep learning model as an input, and then how many like different shapes of, how many different diverse ACC I should put in the system, and what's the resource I should allocate to this diverse ACC are taken care of by our design framework. So all those like code generation, design space exploration has been taken care of by Charm framework. I'll skip some of the detail here, but then if we as the like a software developer, we're always curious about how many lines of code I have saved by using Charm, right? By using Charm, the input is just a few lines of code to describe the model. That's it's a PyTorch or TensorFlow to describe the machine learning model. But then you can generate a code in terms of thousands of lines of code. So these are the design efforts. If we want to start from scratch to write the accelerator, this flexible circuits design that map on those chips. So we actually greatly improve the productivity and also greatly reduce the programming effort when using those ACAP chip. So Charm takes all those like AI models as an input described in PyTorch, and then also we allow those these users to give me those hardware constraints. For example, in this case, I would reserve 50% for sensor signal processing, and reserve another 50% for those deep learning inference. And I can also do that. And then this Charm framework take care of all those exploration part, and then we'll generate the final bitstream. That is you can kind of think that these are the programs that can be downloaded onto FPGA, and then click run, and then that will run those program. So that's the input and output, and then Charm is the compiler or this framework we develop in between. So in order to achieve that, we build those Charm framework in such a way that in a layer fashion. So we first figure out what is the basic code generator unit we need to put there, and then with those basic code generator, how we can determine those parameters that feed into those code generator, and then together we do those full system design space exploration, and then generate the optimized design for this deep learning model. So if I was given another deep learning models, then I can redo this design space acceleration and generate another optimized circuit for that model. So we can have this flexibility if we are switching from this vision transformer, large language models to vision transformer, then we probably can have a different design because they are customized to that model specifically. But some high-level idea is that some high-level idea behind the scenes that we first need to do some, let's say, accelerator analytic model. So this analytic model is that given these different machine learning models, then if I was given certain hardware resource, then I need a optimal design point. So these are just one illustration to say that given those certain input, including those algorithm input and also including those hardware input, I can have multiple or candidate hardware. And then which one is the best? If I want a design within certain, let's say, hardware constraint, less than 70% of the total chip utilization, and then give me the optimal throughput design point, then this green one is the best one. But then if now the hardware constraints are less than 30% of the hardware resource, and then the highest throughput one, then the blue one is the best. So this is like a single accelerator optimization framework. And then with those single accelerator optimization, we can compose multiple accelerator. But then the multiple accelerator, how we can do such kind of thing? Because we have to figure out, first of all, how many number of accelerator I need to allocate to the system. And second is that what's the resource partition I should allocate to these number of accelerator, right? So we have to solve these two questions in this diverse accelerator composer. And then how we can do that? If we think about this as an optimization question, we're basically doing something like how to assign m layers to n different accelerator. If this is an exhaustive search, then we have n choices. So this n accelerator means that I allocate one of the m different layers to this n accelerator, right? So for each n accelerator, I have m different choice. So I have m times m times m, so it's m to the point n, right? So that's exponentially increased, which is not scalable. And then if we want to do such kind of thing for the vision transformer, which has hundreds of different layers, basically we cannot solve this. We shouldn't use this kind of exhaustive search. So we propose a heuristic method, and then we can, based on the assumption that the large size should be good for large ACC and the small size should be good for small ACC, why don't we just sort all those different kernels in the first place based on their shape? For example, in this case, I sort them by their size, and then I can do a hyperparameter setup saying that now let's do search for 2 ACC. And then find an optimized system design. And then I do 3 ACC, and then do 4 ACC until I do not find any improvement. So in this case, let's start from 2 ACC. If this is 2 ACC, I can propose a different partition in terms of those kernels, right? So this is a one partition with 4 kernels grouping in one group. Another one is 4-1 partition. Another proposed is that, and then we can feed those different ACC and also hardware resource to the single ACC model, and then we can give one system throughput. Or I can propose to use 3-2 instead of 4-1 and still feed those analytical models. And now I can get a better one. So this one achieves a better system throughput compared to the previous partition. And I can keep doing this and then until I search 1-4 and then find the best one. In this way, we actually can do such kind of thing in what's the complexity in doing this example. So this is just to do C, M, N, right? So that is we pick this how many number of partitions out of M different layers, right? So this is a much better than the exponentially complexity search algorithm. So that's actually how we can do such kind of we can do such kind of DSE, design space exploration, within a very reasonable time. So we launch this, and then we can find this optimized design, a quite good optimized design within, let's say, 10 minutes search time. And then we can then use those outputs parameters and then generate the code based on this search result. And then we use this charm framework to accelerate 4 different applications. One is a BERT large. This is a natural language processing. Another is a neural collaborative filtering. This is used in this recommendation. And also the vision transformer. This is for MLP, multi-layer perception for classification, the regression. And then I think I have shown something about the vision transformer, which has a huge shape variance. Whereas a BERT is also natural language processing, also has a very huge like shape variance. However, for those MLP, I would argue that's very regular, like all large matrix, and then NCF, most of them large matrix, only one layer of small matrix. So yes, from all those 4 different applications, which one can gain the most from using charm before versus after? This one or this one? It should be VIT, right? Because VIT is the one that has a huge, or the largest variance in terms of those shape, and then it can potentially benefit from charm by the most. So that actually matches our results. So here is the before and after. So one monolithic is that before using charm, and then one specialized is also before using charm. Then the 2 diverse after using charm. And we can also explore this, let's say 8 duplicate, like from 2, instead of 2, I can use 8. But then charm basically opens the door to explore all those diverse ACC design. And then from all of this 3, 4, 5, which is the 3rd bar, 4th bar, and the 5th bar, let's check out the 5th bar, which is the best configuration. And then charm achieves 5.3x compared to the baseline on one monolithic design, and then 32x versus in the VIT. So that actually matches our expectation. But then for the NCF and MLP, well, they have very like little variance. Actually, the one monolithic accelerator can do a pretty good job. But so this is the charm. How can charm find these best combination or resource partition of this chip, and then generate the design based on those parameters. So that's charm, that we can do such kind of like a mapping solution on using those ACAP architecture. That is a heterogeneous SoC with a Tensor core and FPGA, right? But then we haven't come to the point that how is this better than GPU? Why? This is where does that 10x energy efficiency come from, right? Which I'll explain a little bit more here. So if we see those end-to-end deep learning like model, if we take a closer look at those end-to-end deep learning model, and by the way, charm has is a first publication we put in this line for research. Now we have a few papers from this study, and then charm is the first one, and then we want to solve, okay, we solved this matrix modification acceleration. Now we want to solve this non-matrix modification acceleration. And then I want to solve this, let's say, this model size, which can fit on chip. And then this is actually covers that fold. That is, what if like those model size is small enough, and then we can put all those kernel size on chip? Because let's say this FPGA is now has, let's say, 30 megabytes, which is a pretty good like size in terms of the machine learning model. 30 megabytes can, the vision transformer that we use nowadays for those pedestrian classification or this object detection is around like same scale. So it's like a few tens of megabytes. So that's very like a good range of deep learning models we are targeting at. And then if that's the case, then how about we put the architecture design, we can read the data from the first layer once, and then all those intermediate data stay on chip. We don't necessarily need to send out back and forth of those data. And then all the data sit in the chip, and then we can greatly reduce the time spent in the off-chip communication. And that's actually where we achieve those huge latency reduction and also 10x energy efficiency compared to GPU. Because in GPU, we do not have such kind of flexibility without like underlying like hacking on those PTX layer. PTX layer is the assembly layer. You can kind of think of as GPU assembly language layer. But then in the CUDA, we cannot have such kind of control to say, okay, I want to keep this data on chip. Do not evict this data. GPU doesn't have that kind of programmability to user, but whereas in FPGA or in ACAP, this platform, we have such kind of control. We have all those programmability. So that can allow us to do acceleration. First of all, to do all those deep learning kernels, including the non-matrix multiplication kernels and also matrix multiplication kernels, and also on-chip forwarding framework. So I'll skip some of the detail, but the thing is that they have those layer normalization or batch matrix multiplication kernels, which needs huge, which has very less data reuse, but also, so these are some discussion about not only we need those throughput-driven design, we also need to meet the latency requirement. That is what's your application? How fast I should expect my data back, right? And certainly in Tom's driving or the video conferencing, the latency requirements are different. I'll skip some of the details here, which actually are the sequential or spatial architecture. These are some of these data flow discussion when we design these AI accelerators. We have many design choices, but basically there are two. One is that just using this whole resource as one accelerator and call them sequentially, as I just explained. But also we can design those spatial accelerator. Spatial accelerator means that if I have, let's say, 4 layer, and then I will just allocate 4 accelerator. That this is a one-to-one mapping spatial accelerator. But then you can kind of think that they're intermediate state, right? I can map like a field to one, which is similar to charm. But in this case, is that we want to do the design which meets the latency requirement while still achieves the optimal throughput. So this one, we put more latency requirement into the design space exploration. And that's exactly this chart shows. So this is the one, the x-axis is the latency, and the y-axis is throughput. So we want the design which achieves the lower latency and higher throughput. So the better design sits here, right? But then this chart is the spatial accelerator. This chart is a sequential accelerator. So with different like latency requirements, they actually give, it's not the case that the sequential accelerator always win over spatial or vice versa. They can be like the best design choice under different latency requirements. But our design actually achieves a better latency throughput Pareto from, which means that we can achieve a design which is better than all prior sequential or spatial design under the same latency, a higher throughput, or let's say a lower latency with minimum throughput requirement. So that's our design choice. So we have a more flexible design and also achieved a better latency throughput Pareto from. I'll skip this part. That is how we achieve that. But I really want to highlight I'll skip this part also. This is the architecture which shows that where we put all those matrix accelerator and where we put those layer norm, softmax, transpose. These are some data reorganization kernels on FPGA. So we make the best of both worlds. We have those Tensor core for AI heavy kernels, but also we have FPGA that can compose all those newer, or let's say in the future, we have another function, and we also want to map those to FPGA. We can always use programmable logic to fulfill the task there. So these are some of the data flow. And the highlight part is that we have those on-chip data management systems so that we can keep the data as long as the data fitting on chip. So we can always cache the data without kicking them back and forth to off-chip DDR when switching from one kernel to another kernel. And also we allow those, let's say, this is very specific to FPGA. That is that if we have a kernel, let's say these are 3 kernels, HMM, and then after that, this is sorry, I should say this. Yeah, so this is a 1 HMM kernel, and then following this kernel, this is another average and also another kernel. So in total, we have 4 kernels. If this is a GPU programming like model, then we'll call one kernel, another kernel, another kernel, another kernel, right? Whereas in FPGA, as long as the data is ready on chip, I can forward the data to the second kernel that we implement on chip, and then it can start to do computation. So this is what we call fine-grained pipeline or this data flow architecture. So as long as the data is ready, then let's start the computation. So that greatly reduces the latency. So from here, we have to do this, but then here we have this reduced latency. So all these are the techniques enabled by using our framework and also provided by FPGA. So this high level, this one shows a comparison about how we can achieve a better like throughput on the same latency requirement. Whereas in this case, this line is the sequential design. This line is a fully spatial design. This one is the design where we consider all the cases in between sequential and spatial, and then we achieve a better throughput, let's say under the 0.5 millisecond latency. All the design points left to this 0.5 are valid design point, and our design is the best that achieves a higher throughput compared to these design points. Where's GPU? Okay, GPU is here. So this is the measurement when we deploy using the latest Tensor RT. That's the GPU provided compiler to compile those deep learning models onto this one. I believe it's Orange GPU. And you see the latency here versus the latency here. We have around like 3x difference in terms of latency. Not to say that this one it needs a higher like power, and whereas this one is around like 30. Sorry, this is around like 50 watts of the power, whereas this one can be as high as 100 watts. So we have higher energy efficiency. Considering in this case, I think 8x to 10x. So to summarize, we have this sequential spatial accelerator, which allows us to do all those fine-grained data flow pipeline architecture, and also allow us to greatly reduce the latency when executing all those end-to-end deep learning inference. So here, this is actually the end-to-end latency breakdown of all different kinds of computation, including those matrix multiplication. The patch embedding is also similar to MM. And then BMM, that's a batch matrix multiplication. Reformer is just data layout, transpose, and then all the kernels. So this is like the breakdown for GPU execution. Whereas here, that's our execution. So first of all, the most time-consuming part is also the matrix kernels, right? But then the other kernels, since they are all running in parallel with those Tensor core, we can overlap their execution time and then hide hidden by this when executing the matrix kernel. So that's how we can greatly reduce the latency. From in this case, it's 1.78 millisecond to 0.5 milliseconds. That's the 3x. So sorry, this GPU is A10G. That is the desktop GPU, Ampere architecture, and then that's how we achieve those 10x like energy efficiency. So that's the underlying accelerator design. I hope I give you some like idea about, okay, now we can do like AI accelerator mapping on using the latest FPGA plus Tensor core, and now I can do a better job in terms of energy efficiency, in terms of latency reduction. But then in terms of why does this matter? How can we, for example, can we use such kind of thing in autonomous driving vehicle, and why is needed, right? Why is this needed? So one thing I think I can also, this is the latest research results from collaboration with Dr. Dong, is that in real-time systems, so this is I put a graph from our presentation, that is a real-time system. So in real-time system, we have multitasks, and these tasks are generated or released in periodic fashion. And those tasks need to be finished by the deadline. The deadline is usually, let's say, the next new task has been released. So they have those deadlines. And then if you miss the deadline, it means that if I cannot finish this execution before a certain deadline, it means the whole system fails, which is not good. And all the accelerator I just discussed is good, but then the thing is that it's not compatible with this real-time system if we do not do further upgrade or optimization or let's say modification. One thing is that if I launch, let's say, end-to-end application, end-to-end vision transformer, think about that. This is a task 2, which is a vision transformer task to do classification. If I do not have any preemption means that I can stop this task and then resume this task later. If I do not have such kind of preemption mechanism, once I launch, I can only swap to another task when it's finished, right? If that's the case, which is our baseline accelerator, which is like before this work has been published, then it could be the case that we miss the deadline. Miss the deadline means that system fail. there are two ways to improve this. The first of all is that I can reduce or keep reducing the latency to do this task. And then to some point, it could be like reduced from 200 milliseconds to 40 milliseconds, but still miss the deadline. Or let's say in other cases, the deadline is very short, and then I cannot always improve the system schedulability by using this way, because I cannot, there's certain hardware limit, right? I cannot reduce all those latency to faster than light. I cannot do that, right? But then the correct way, or let's say the real-time system way, is that we support this mechanism of preemption, and then I can preempt the task when needed. So this blue task now has a very strict deadline. I need to finish that. So if that's the case, I can preempt this yellow task and then allow this blue task to finish the second job and then resume back to yellow. But then this yellow task has been swapped, preempted again, because there's a third job of this higher priority task has been released. I need to finish that one, which requires our accelerator system to support preemption in the first place, and also without introducing huge overhead. If we are introducing huge overhead in the preemption themselves, then we're probably introducing too much overhead, then also will cause the system failure, right? So we need a system that, first of all, to support the preemption, and second of all, deterministic overhead, or let's say very overhead that we can apply in the schedulability analysis. So this is the accelerator system we just designed. Well, the high-level idea is that this part is whatever the accelerator we just mentioned, like charm accelerator or sequential spatial accelerator we just mentioned. But then we definitely need this mechanism to support the preemption. So here, the preemption, that is this part. So we first of all need a scheduler that can allow this accelerator to know that, okay, which task I should schedule now. And then the second part is that what information I need from those tasks, including those task deadline, including those the shape that this task should finish, to those information. And then we can send those control information to this existing accelerator we want to do. And what's different from the system compared to the, let's say, CPU FPGA or CPU AI accelerator platform? So previous work, they put all those scheduler control in the CPU side or in the host side, whereas we implement all those control logic all on hardware, on the circuits. So that is how we can enable such kind of a preemption. And also with this scheduler implement on chip, we know exact number of cycles we need to finish the scheduling, and then we know exactly how many number of cycles when we preempt a certain task. So that's the beauty part of why we implement this in the hardware in the first place. And these are these input task information, whereas these are how we configure the platform in the first place when given certain set of tasks. And these are some of the low-level details about how we design such of a controller, and then what is the FIFO we need to design so that we can take the input from the sensor, let's say from off-chip. If these are sensor input from LiDAR or let's say camera, then we need those FIFO streams to take the input from the outside, from the sensor. And these are where we take into those task information. And this is this very high-level idea about the scheduler and the accelerator, how they communicate to each other. So we need the scheduler to tell the accelerator now what task you should do. And when the accelerator finishes certain jobs or certain region within a job, it needs to provide the feedback saying that, okay, now I finished certain jobs, you can go ahead to schedule another one. So these are all implemented in FPGA. And coming back to that question, how we can implement such a control-intensive workload on FPGA? Actually, that's also doable. Compute-intensive kernels can be done on FPGA by using high-level synthesis. Control-intensive can also be done in high-level synthesis. So actually, this is exactly the code we write in high-level synthesis C to enable such kind of a loop-based schedule, loop-based, or this is feedback, not loop. This is a feedback-based control circuit system. I'll skip some of the detail, but then you can kind of think these are these FIFOs to talk between those accelerator and scheduler, and then we can probe whether this FIFO is empty. If it's not empty, it means that there's a new task now. I should do something, right? And then this is well, the feedback means that, okay, if this feedback FIFO is not empty, it means that I have finished one task already. I should allow scheduler now to give me a new task. So all those like a detailed implementation now can be described in high-level C. So these are all the code we actually like design in the system. And then this code will be compiled to the RTL code and then enable this cycle level accurate control system on chip. So with that saying, I think I will conclude today's presentation, but feel free to ask me any questions. Yeah.
Also, you mentioned using the FPGA is much better than GPU in terms of latency and throughput.
Yeah, yeah.
So then the question is, okay, what's the cost? Right? What's the cost if you change from GPU to FPGA?
So the cost, first of all, is the programmability, which has been kind of solved by some of the latest efforts in our group. But then the thing is that, think about how we program GPU. We do not even need to write any C code nowadays, right? We only write Python code. So you just describe a machine learning model in Python, in PyTorch, and then we'll compile the code to the GPU and then run that. Then if we still need to write C or C++ code to describe those accelerators, it's not still that like high level. So one of the work that I haven't mentioned here is actually published this year. We provide a Python interface to allow users to compile the code to FPGA by using Python, just writing Python code. So this is published in this year FPGA 25. We can allow users just to write Python for loop and Python like to describe this deep learning kernels. We have tested that for CNN-based models and also for transformer-based models. And then we're now exploring using Python code to describe all those digital circuit, the digital signal processing kernels as well, and also including image processing kernels. So we are still working on that. But I would believe that with this programming effort, like all those like compiler design ready, I think the cost to switch from GPU to FPGA will be greatly reduced. Yeah, but the programmability is one thing I have. I think it's a very it's an important issue we have to fix. Yeah. Thank you. Yeah.
Sorry, thank you for the presentation. I just want to clarify on the architecture of the SSR platform. So essentially, we put FPGA with Tensor cores together, and when you analyze the machine learning models, you break down the layers into how you break down the layers into how the layers and the nodes are controlled. So what nodes get activated, what weights get updated, and stores that logic in the FPGA gates. The tensor cores will do the matrix multiplication, and you switch the. So in the GPU, you have the VRAM to hold the data, but now you're using the
on-chip RAM. Yeah.
The RAM.
Yeah. VRAM. Yeah.
Yes. Okay. So then that way you can speed up the process because now you're only just using the tensor cores to do the multiplication, because the FPGA lookup tables will support parallelization. Then you can parallelize the models inference and training process.
Model inference and the what?
And the training process.
Training part, that's another thing. Yeah. So,
so
this is all for inference. Yeah, for now.
But,
yeah.
but the logic that I described is correct.
Yeah, yeah.
Okay, thank you.
I think William has summarized my talk in a very beautiful way. Yeah. So first of all, the tensor core and the FPGA can run in parallel. So that's how we can overlap the execution of those matrix kernels and on non-matrix kernels, because we are actually running different pieces of the hardware. And second fold is that we have those BRAM, which is on-chip RAM, so that allow us to feed the data the tensor core needed from the FPGA and also from tensor core back to FPGA on-chip RAM, so that we can greatly reuse all the data on chip. Yeah, which GPU nowadays couldn't allow us to do this.
Could you go into a little bit more detail on how you divided the layers into different lookup tables on the FPGA? Did you?
Oh, in different lookup table, that's actually a great question. So that's not the level that we, first of all, how we use the different lookup table or different, let's say DSP, maybe I can explain this part. So if I have I have one kernel in softmax, I have another kernel in layer norm, right? Then they all need some computation resource. And I, as the programmer, I need to guarantee that the consumed DSP, which is a compute for those MAC operation, and the resource, let's say, to do those control shouldn't exceed the total on chip like resource. So we have some like a performance and resource model to guide us this design, so that we can know, okay, I shouldn't do those huge parallelism because that will like exceed all those on-chip RAM resource. So we need that kind of like resource estimation, yes. And then if, let's say, the system fails because, not system failed, but the implementation, when we generate the bitstream fails because of this over allocating resource, then we have to reduce this accelerator size to the proper parameter, yeah. But these are all like a design space. I can design a small ACC or I can design a huge ACC. Yeah.
But this wasn't done manually.
This is done automatically. Yeah. Yeah. Good. Yeah. You should come here and then we can explain you to more in offline. Yeah.
You, Professor, for the presentation. That's really interesting. And my question is, from the scope of commercialization, is there any advantage to use FPGA versus GPU to achieve like similar level of
Well, I guess to answer some of this question, I need to explain a little bit about commercialization on FPGA using AI. Those kind of things is already there already. So there are many companies using FPGA for AI edge deep learning acceleration. Yeah, these are like FPGA without Tensor core. But I haven't seen, because this is I think a pretty new like architecture. It's being released in 2019, but then the board actually we received that it's after 2022, we got the board. So we will see more and more this kind of like let's say startup companies using this platform. But I'll give you one example is that the algorithm changes. And then the algorithm might change in a way that this like the GPU instruction in Tensor core or this vector instruction cannot support that kind of computation. And then if that happens, and then GPU, I have to use a CPU, fall back into CPU to calculate that kind of thing, right? But then in FPGA, I can still use a circuits, or very like customized circuits to compute that kind of new type of computation. So then I can, without changing my hardware, I can still achieve a great performance. That's why we need FPGA in all those, let's say, space computing in the first place. Because once I launch that, how can I guarantee that it's working for the future application as well, right? So that's just one example. Yeah. Yeah.
So thanks for your presentation. So recently from our work we deployed the model on the Orange JSON AGX, and we found there's some issues with the optimization. And you mentioned you have the tools just published, and you have the reduced codes to transfer the Python code to the C++ FPGA, which can run on the very smoothly. And if we bring the attention mechanism and mix it mixture to the convolutional traditional network, so does your tool still working on the FPGA, or you are just using the purely CNN based or the transformer based? Thanks.
Okay, so we have verified our, like, say, the PyTorch, sorry, we have verified our work. It's called ARIS. This is a framework that's compile the code from Python to FPGA for being transformer, for this loop, massive for loop benchmarking in Polybench. That's our like massive for loop code. For CNN, it's actually 7 layers massive for loop. We haven't tested that, but it should work.
First transition to multi, so I think both hardware and software community will scale, right? So especially software, because of like how do we program this, and then we provide hardware level parity, yes, right? So now what's the solution? So that time Intel and Intel and Microsoft is okay. each of us will chip in like $10 and $15 million. So then we pick two universities to solve this problem in UNC and stuff. Right? So of course one of them failed. So I really got half the money, and I believe only half of this. But one of the solutions is from a general programming point of view, because they always scare you. So how about when you introduce you don't need to build a parallel, but we introduce a parallel library, right? So then when you write your code, instead of calling the conventional split library, you just make the call to the parallel library, right? So that which solve the problem.
Yeah.
Right. So now does that similar method applies here, because right now, like how do we really solve the general programmability from high level code to FPGA, right? So that means so you can do very customized. However, it seems sometimes program ease for programmability is more than the very tailored to that. So that do you see the solution is like I provide a library in terms of accelerator-based FPGA design, right? So that way, that could ease my solution in terms of high-level translation from the high-level code for these ML algorithms towards effective.
Yes, exactly. That's actually AMD in the first place commercialized this project already. So we can provide library only. So that is one accelerator system that can compile, that can actually run without reprogramming the FPGA, but run any deep learning model, because they're just a CNN or vision transformer. So they can do that. But then the performance is this one. So I can easily use this one like a library. So there are existing solution already, like using like exactly like this way. Or I can use this one to compile customize that. But I do agree with you that we should provide a library with the same performance without recompiling this whole thing. Yeah,
So that's
I agree. Yeah.
Yours.
Yeah.
Yours replace their library.
Exactly.
Have the best of both worlds.
Yeah. So thank you, Professor Liu. Actually, one of my students working on this, that is proposing some overlay architecture without reprogramming, but then they can adapt as if like I can this time I can do this if I choose, or I can do like a flexible 2 or 4, but that's with dynamic like data merging or splitting. Yes, we are working on that. Thank you. Yeah.
Ask the final question. We'll end this picture.